stars. Maybe everyone's going to see stars now. So I'm going to first talk about our solar neighborhood. Now that we've gotten things down to scale, I'm going to squeeze the nearest stars into a little diagram to show where everyone lives. And then we'll start talking about the patterns of when we look at different stars, what sort of patterns they fall into. And we organize that into something called the Hertzsprung-Russell diagram, which is named after the people who did it first. And then we'll talk a little bit about what's going on with different stars. So this is our neighborhood here of the sun. And our solar system is right in the middle. It's in red. And we can see the nearby stars to the sun. And for the most part, you won't be familiar with their names, right? So like you can look over here. This is called Gliese 317 or HD, blah, 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 blah. And those are they're relatively faint stars that you can't see with your naked eye, right? So we don't have them. We don't have familiar names to it. But the sun is right here in the middle. And the star that I was talking about, the nearest star to the sun is this guy right below, Alpha Centauri. And Alpha Centauri, the way this diagram is done, north is up, right? So Alpha Centauri is down. We can't see it from this part of the Earth. It's a relatively bright star. It's not the brightest star in the night sky, but it's very similar to the sun, except there's 3 stars together. So one star is a little bit more massive than the sun, and it's being orbited by another star that's a little bit less massive than the sun. And then there's a third star who's even less massive than the other 2. And we think that that third star, which is in fact the closest, has a little planet orbiting it, just like we do. Now the stars that we can see from here that are maybe familiar in our night sky are Vega and Altair, which are generally in the evening. They're almost overhead here quite often in the year. How would you know what they are? Maybe it's difficult to tell you. But if anyone's looked in the sky, there's a big thing that looks like a cross. That's Cygnus. And it's often right overhead. And Vega is just to the right of Cygnus, and Altair is just to the left of Cygnus. But then other stars that are nearby that are interesting are Arcturus and Aldebaran, which appear yellow. So Aldebaran is in the horns of the bull, and it's this yellow star in there. And Arcturus is in Bootes, whatever Bootes is. It's Bootis. Bootootis. I have no idea what that means, but it's in this Bootis. But then you look below, there's a star called Sirius, which probably every one of you has seen. In this time of year, in the evening, it's in the southern sky over there, and it's really bright. It's the brightest star in the night sky, and it scintillates. So when you look at it, it looks like it's changing color. As you move around, people think it's following them because it's far away. But since it's changing color, people think it's like an airplane. So people will go, oh, there's something following me. And I'm driving and it's still there. It's still following me because it's a star, right? It's not following you, but it's so bright that when you look at it, you see this scintillation. So people think it's like the changing colors of a plane or an alien. Okay, but a lot of the stars that you see in the night sky aren't that close to Earth. These are just the nearest stars to Earth going out. I have to guesstimate how. So this first ring is maybe 5 parsecs, 10 parsecs, and 15 parsecs. So one way to find a nearby star is look for stars that move across the sky really fast. And this is a famous one called Barnard's star, who, if we look in the previous picture, Barnard's star is right here, very close to the sun. And if something's close to the sun, if it's moving like this, it'll appear to move across the sky really fast. Whereas something further could be moving even faster but look slower because it's further away, right? Does that make sense? So this motion across the sky, we call it proper motion. It means the motion across the sky. Barnard's star moves 10 arc seconds per year, or about a quarter of the full moon in a lifetime. So, it's relatively easy to see it moving with a telescope. It's too faint for you to see with your naked eye. So all of the stars, in fact, are moving with time, right, relative to the sun. So the shapes that we think of constellations now, like the Big Dipper, 10,000 years from now, they'll look different, right? They'll look somewhat different. And even later, they'll be completely different. So over the time scale of the constellations, they're just temporary patterns that we see right now for the most part. There are some stars that are actually associated with each other, like the Pleiades, which maybe you've seen. It's near the horns of the bull of Taurus. That's a cluster of stars that's all bound together. And it's been bound together for about a couple 100 million years. So earlier, it would have appeared in a different part of the sky, but those guys would have still been together. They would have rearranged, but they would have still been together. Similarly, the Big Dipper, those stars are all actually associated with each other, a lot of them. So they might have changed their shape, but they moved together, believe it or not. So if we think about how a star can move, it can move across the sky, which we call the proper motion, which is measured in angle per time. And it can move away from us or towards us. And for stars going out to distances of thousands of parsecs, we can measure both of these quantities. We can measure how fast they're moving across the sky and how fast they're moving towards us or away from us. Do anyone remember how we measure how fast they're moving towards us and away from us? Remember how we do it? What? No one's guessing. It's only a little bit harder than 1 plus 1. It's called the Doppler effect, remember? So the frequency of everything, or the colors change by a little bit. So we can measure both of these things and see how far it moves. So the second nearest star, what's the first nearest star? That's another easy question. It's the sun. It's the sun. The second nearest star is the triple system of Alpha Centauri. And there it is, up there. There's 3 stars in it. So this is looking into the sky. Here's the 2 of the stars are here. The third star that we think is bound to them, and it's the closest, is way over here, and it's really faint. These 2 stars are quite bright combined. One, like I said, is a little more massive than the sun. One's a little bit less massive than the sun. And the third star is just this little dot there, right? And how do we know? Because people, it's not that faint, but they notice that star, of all the stars, has the largest parallax of any star. So we know that that's the closest, that little faint little smudge. And there's a wide range in how bright objects appear to us, right? From the sun, from Earth, all the way down to the limit of the faintest objects that we can measure with the most sensitive telescopes. So on our chart that I gave you, it doesn't go to 30, it goes a little further, 31.5. And the reason why I know it's 31.5 is because I gave you this chart, which we'll look at in a little bit, and it goes all the way down to 31.5. So this is data from my research group. So if you ever want to know what are the faintest objects ever detected, well, it's on this sheet, okay? And that's with the Hubble Space Telescope looking at the same part of the sky for about 2 days. 2 days straight, meaning it observes for like 4 or 5 days because it can't see it the whole time because it orbits the Earth, right? So a really, really very sensitive observation. So when we want to think about how bright a star is intrinsically, we have to factor out the distance part of it. And when we get to this one called Hertzsprung-Russell, the distance, all of these stars here are at the same distance from us. And that's why this is a useful way of thinking. We know they're at the same distance, so when I plot how bright they appear, that is related how bright they are, at least relative to each other. So we talked a little bit about this. So we can think about how bright the stars are, but we can also think about what color they are. So we have 2 examples here. On top is the constellation Orion, which I think a lot of you have seen, or I hope you've seen. And you can see just by your eye that there's a red star up in the top left. That's Betelgeuse, which means like the armpit of the giant. That's what it means in Arabic. Because Orion is like standing like this. There's like a shield here, and that's where Betelgeuse is, believe it or not. And then the one down here, the foot, which I guess is this foot, is Rigel down there. And that looks really bright and blue. And if you look at the other stars in there, the stars of the belt are even bluer than Rigel, if you look at it carefully. They're even bluer. There's also this fuzzy thing, right, which isn't a star at all. That's the Orion Nebula there. Now, to the colors of stars correspond to their temperatures. So Betelgeuse is a cooler star than Rigel, and you can see it with your eye. Now down below is a whole bunch of stars in a cluster of stars, and I'll show you pictures of that. In fact, I'll show you a picture of this cluster of stars when we start doing that one. And there you can see a whole bunch of stars of different colors all at once, not spread over a huge area of sky. So we like to quantify what does color mean. What it means is how much light is, let's say, coming at the blue end compared to the red end. That's what color is. It's the ratio of light at the blue end to the red end. So how could we do that in magnitudes? It's just the difference between the blue magnitude and the red magnitude, for example, would give us an idea of the color, right? Because remember, if we take a difference in magnitude, that is a ratio of the actual brightness, okay? So if we think, I have a whole list of the different colors that we would see. So an O star, we give them letters, right? So O are the hottest stars, and then B, A, and so on. And there's a historical reason why they don't seem to be in order. So you can remember this, and it's in your book. You could say, O, be a fine girl or guy, kiss me. Will get you down to M. And then LTY, I have no idea, right? We won't worry about that. Whatever. Okay. So, and there are a bunch of examples of stars. So a blue star, we have there Menaka, which is one of the stars of the Big Dipper. So the stars of the Big Dipper are all actually together. They were all born together, and they're what's called an OB association, which has nothing to do with obstetricians. It means that we have O stars and B stars that are all relatively young, we'll learn, and they were all born together. So Menaka and Akhtarnar, for example, and Mizar are all O and B stars that are in the Big Dipper. So these stars here in the belt are bluer than this guy, and they would also be O stars, where Rigel is a B star. And then we go to stars that are less blue, stars that we might think of as white when you see them at night. That Sirius is a white star as you see it at night, and so is Vega. Yes? This is the temperature at the surface. Does that make sense? So, Procyon, I don't know if you guys would know this, but then as we go to stars that are cooler, with your eye, you'll see very few stars that are actually yellow, like the sun and the night sky. They're relative, and there's a reason for that. But it's not that they're rare; it's just that they're faint. As you get to stars that are burning hydrogen in their middles, as you get cooler and cooler, they get fainter really fast. So then we have orange stars like Arcturus, and then the red star like this guy, Betelgeuse, right? And those guys are doing something else inside that makes them much brighter than a star that's burning hydrogen in the middle. So the colors of the stars are giving a hint to what the stars are doing at that moment. So another way of looking at these colors is if you didn't have color vision, what you could do is look at what spectral lines appear. This is in your notes, but here it's better to see it as in a picture. As you go from really hot stars to really cool stars, you end up seeing more and more spectral lines and different sorts of spectral lines. And way down in the bottom, you see tons of stuff. And that's because these stars are actually forming molecules in their atmosphere.
The spectral type, it turns out, is very much correlated with the color of the star. And you have to think that maybe at the time these two were separate things, but there's a reason why they go together. So what the spectral type meant were these letters that people came up with, where A were the stars that had the strongest hydrogen lines, the lines of hydrogen, which are these guys right in here. Bam, bam, bam. So in here, those hydrogen lines are the strongest. And as we go to spectral type B, had the second strongest hydrogen lines, and then so on. And there were some letters that got removed later. You can see it goes A, B, F, G, K, M. It wasn't that the astronomers tried to make this really difficult for people. They just ordered them in the order of how strong these hydrogen lines were. And it turns out that that wasn't the best way to go about it. So what we've done here is at the top, I've put the hottest stars. So the hottest stars are O, and the coolest stars are all the way down at M. And you can see this if you look at those rainbows with your eye, or at least I get the sense that the brightest part of the rainbow is going from the top left to the bottom right. And if you remember, the peak of the spectrum corresponds to the temperature. So the one at the top is bluer, and the one at the bottom is redder. Now, the idea is, as the temperature of that layer of the star changes, the atoms that are excited to make the lines and make the absorption lines change. So it turns out around 10,000 degrees, which is those A stars, is when you have the largest fraction of hydrogen atoms in the right place to form those lines. So in hydrogen, those special lines correspond to, there's a hydrogen atom, and the hydrogen atom has one electron, and it's not in the lowermost level, it's in the second level. So let's see one of these hydrogen lines. They're all the way over there, and the red is one of them. So this hydrogen line over here corresponds to the electron going from the second level to the third. And then this one, I think, is the second to the fourth, and so on. So for it to show up like this, you have to have a lot of atoms excited into that second level. And that's why when you go to colder stars, the lines disappear, right? that line where my arrow is, as I go down, it becomes weaker and weaker as I go down to cooler stars, because a smaller fraction of those atoms are in that excited place. Now, if I go higher up, you can see it gets weaker as well. And that's because those hydrogen atoms, it's so hot that the electron just goes away. They become ionized. So as I go to the top, even though it gets higher in temperature, the electrons get too excited, and they don't spend time in that second level very much. So as we go through these different types, we have different sorts of elements are excited, different molecules sometimes, and different chemical elements in different states. So if we look at the top, that's the coolest star. You can tell it's the coolest because its spectrum is going up towards the red. And you'll see there's things like calcium, right, and magnesium. But everything else here are molecules. So this is titanium oxide, vanadium oxide. And what are these things? Titanium oxide, it turns out, is what makes the paint white. It's just a common, titanium is relatively common, oxygen is relatively common. In a star, they get together and they make a molecule that creates all of those features. And then if I go to a hotter star, the K star, that's a bit cooler than the sun. You can see in the K star, this is like maybe 2,000 degrees, this is maybe 4,000 degrees. There's no more molecules, right? The molecules are gone. And the lines of the atoms that we see are from the atoms in the first two columns of the table, right, over here. So we have sodium and magnesium, we have calcium. And those atoms in the first column, up, they're both relatively common, and their electrons are easy to excite. So that's why we see those spectral lines. And then when we get to G, we first see the hydrogen lines. Here's one of them, and there's one of them. And that's like the sun. The sun is like G2 or so, and that's what a solar spectrum would look like. Our A star, about 10,000 degrees, the main lines you see as advertised are those hydrogen lines. So this is an electron going from 2 to 3. The next one over is 2 to 4, 2 to 5, 2 to, and so on. And eventually there's lots and lots, and above that point where the arrow is, the electron can just leave the atom. And that's why when the star gets hotter, those lines actually get weaker. The bottom one is the hottest star that I have on the list. And it says O5. That's a star maybe 20 or 30,000 degrees. And we see lots of lines of helium now. And the funny thing, and this is maybe something to look at, it says helium-2. And what that means is the helium has already lost one electron. That's what helium-2 means. That's what the 2 means. Calcium, the other one is carbon-3. What do you think that means? Carbon-3 would mean the carbon has lost 2 electrons. I know it sounds, we didn't make this up. This is the sort of people who study spectra made up this. So if the atom hasn't been touched, hasn't lost an electron, it has a 1 next to it. If it has lost a single, it's 2. As far as what do you need to know, we're going to talk about things called H2 regions. And those are regions where the hydrogen is ionized. So I'll use that terminology, H with Roman numeral 2. So you won't have to remember that, but I'm just telling you just so you know. So here's just a table that is outlining or reiterating what I was saying earlier. We have all these spectral classes that go down to M, and then there's other ones. As the stars get even cooler, they aren't necessarily maybe stars, they may be brown dwarfs, and we see other molecules showing up, and that can dramatically change how the star appears. That's why we call them brown dwarfs. Like brown is like, it's not a color of the rainbow, right? It's not even a color of a black body. These stars that are much cooler have so many molecular features that their colors look really weird. And we gave them letters L, T, Y. Don't know if it goes any further. So that's a basic thing we can measure about stars. We can measure their color. We can measure how bright they are. We can also make a table of what the spectral lines are that appear, and that covers those aspects, the spectral types. Now, if a star is in a binary, occasionally, if everything is oriented correctly, one star can go in front of the other star, like this, from our point of view. Just like this morning, the Earth went in front of the sun from the point of view of the moon. And I actually woke up and saw it, the blood red moon, but that was okay. Did anyone else see it? Probably not. Had to be up. You did, and it was clear. The weather report said it would be cloudy, so I didn't send everyone a reminder, but it was clear. And it looked okay. It was cool. I didn't wait to see the shadow go across. I just went and looked, because I'd seen the other thing before. But it looks blood red, right? It's pretty cool. It happens reasonably often, so those of you who missed it, there'll be another chance, but it happens at night usually, almost always. But today it was just as the sun was coming up. Okay. So what can happen is one star can go in front of the other. Now, why is this really useful? Is because if we know how big the orbit is, right, how big the orbit is, and how long it takes, we can calculate how long it took. If we know how long it took one star to go in front of the other, that tells us how big that star was. And when this star goes behind, that tells us how big the other star is. So let's look, right? So if I think about it, it's coming along, and when one star goes in front of the other, you can see that the smaller star goes in front of the bigger star. This slope here is how long it takes the smaller star to get in front of the big star. So that's related to the size of the small star, right? So here, the small star is in front of the other star. So now the other star appears, I have to think about it. No. Okay. When I go behind, this is when the small star goes behind the big star here. It goes down a bit. And so that how long it takes to drop down is related to the size of the blue star. Okay? Now the blue star, every little bit of the blue star is a smaller area, but every little bit of the blue star is brighter than the red star, right? So when the blue star is hidden behind the red star, we're missing the light of the blue star, so it drops down, and it's down here, right? And how long this takes is related to how big the red star is, because that's how long it goes from here to here to here. Okay? Now it's coming around, it's a merge, and it's coming along here, and then now the blue star is blocking part of the red star. Again, the time from here to here is the same as from here to here, because it's the same star that's going in front. But now the blue star is blocking the red star's light. And the red star, every little bit of the red star is not as bright as the blue, so it drops down less. So for example, those decrements, right, so how much this drops, right, how wide this is, tells me about how big this star is going across. How much this drops has to do with how big my blue star is compared to the red star. But you can see, like, by these binaries, you can figure out a lot about the stars. You can figure out their physical size, even though we've not gone there. And you can figure out how bright they are, each of them inherently, even though you don't know the distance. So they're really cool. And And there's a few that are really bright. So one is called Algol, which to think what constellation it is, but we can definitely see it from the northern hemisphere. So it's so dramatic that the star is sometimes blue and sometimes red, right? So one goes in front of the other, and it totally hides the other star. So that's pretty cool. So with an eclipsing binary, we can measure that radius relatively accurately. But for the other stars, we just use the trends that have to do with the fact that they emit approximately like a black body. So the luminosity of a star, if we know that the star is at a certain distance away from us, we can measure its luminosity. And it goes as the temperature to the fourth power times the radius squared. So we can combine those in a way and figure out the radius of the star if we know how bright it is and what temperature it is, right? So here's showing the relative sizes of the different stars as a function of spectral type for the time when they're consuming hydrogen in their middle, and that's called the main sequence, and we'll see that on the Hertzsprung-Russell diagram in a minute. So more brighter stars or bluer stars are typically bigger, right? And the range in mass from down here is maybe 40% of the mass of the sun, and up here is 20 times the mass of the sun. But physically, they don't get that much bigger. They don't get, maybe they're 20 times bigger. They're not so big. But later on in the evolution of the stars can really puff up. So we have these stars called supergiants, and you can see here, there's a picture of the sun to scale and the Earth's orbit, and that's how big the star is, right? So this is the Earth's orbit. This is not the sun. The sun is this dot that we have to zoom in on here to even see. So there's some stars that are physically in radius much, much, much bigger than the sun. So we can have stars, I don't know how big this guy is. It's crazy. I mean, it's probably out to Jupiter or even Saturn, the size of the star if we were to put it in the solar system. So we can also figure out how big the stars are by looking at those spectral lines too. So this is something that's a little subtle. All of these stars have the same temperature, and we can figure out the temperature by the sort of shape of the spectrum, or by how deep is this line versus that line in the same star. But if you look at the stars, as we go from here down to here, these lines get weaker, right? So this guy has weaker lines than that guy, even though the temperature is the same. And if we think about how these form, stars whose atmospheres are less dense will have weaker lines, and the stars whose atmospheres are more dense will have deeper lines, right? And so we can use that to also figure out how big the stars are, right? So I'm just giving you these are just different ways of how we figure things out and that we can measure. So the most basic thing we can do, which is this exercise, but this is not for these stars, is here's a bunch of stars that are in our neighborhood, plus stars that are relatively bright on the sky. And what we have along the bottom is how hot they are, and vertically is how bright they are. So it's the same as this guy. This one is for not stars in our neighborhood, but stars that all live together in a sort of city of stars called a globular cluster. And that city of stars is about 4 kiloparsecs away, so all of these stars are about the same distance from us. But we can look at either of these diagrams, and maybe the key thing that you'll notice is that most of the stars live together in this thing called the main sequence, right? And here's our sun and its neighbor, Alpha Centauri, who are on the main sequence. In this one, the main sequence is right here. There they are. Now, if you look at the diagram a little bit more, you'll see that there's stars that are red, but much brighter than these main sequence stars. So if you remember, they're the same temperature, right? But the ones up there are much more luminous. So what does that tell us about those stars at the top? They're at the same temperature, but they're more luminous. You can also get a hint from what they're called. What are they called? They're called giants, which means that their radii are big. That's how come they're up there. They're at the same temperature, but their radii are much, much bigger. In this one, it's maybe hard, but here, the giants get so bright. But here you can see these guys and these guys are the same temperature, but these guys are much brighter. These are the giants in this guy, and these are the ones that aren't giants, that are along the main sequence. We call them dwarfs. Not to make them feel bad, but they're called dwarfs. Now there's some other stars, other objects here that are down here. And can you find them on this plot? Where are they on that one? They are not, they are the same color as stars here, but much fainter. So what does that mean they are? They are smaller. Their radii are smaller. And those, we call them white dwarfs, right? And they aren't all white, right? So eventually they get to be yellow. So like these white dwarfs in here on this diagram are about the temperature of the sun. So they would look, but they're much smaller than the sun. So the sun, I don't know where I would put, the sun is about here, and these guys are much well below the sun. Okay? So this is what, so a lot of understanding, how we understand how stars change with time, comes from looking at this sort of picture, or this picture, to understand, well, why are there stars? Why are most stars along here? What are these guys doing? And what's happening to the stars up at the top? So it's a lot of what we're going to talk about until the midterm is about why this HR diagram looks like it does. So I talked a little bit about these eclipsing binaries, but I just talked to you about the geometry of them. But let's think about it. If I have two stars orbiting each other, and I know how long the orbit takes, and I know how big the orbit is, I can figure out the mass of those guys, just like we measured the mass of the sun. Right? I had the Earth going around the sun. I knew how long it took. I knew how big the orbit was, and that gave me the mass of the sun. If I have two stars orbiting each other, I can figure out the masses of those stars. So here's a picture of just what a pair of binary stars looks like. And really, you can, with high enough angular resolution, you can see them orbiting each other, right? So it's going around, right? So here it's star, star, and there they are. And then as it progresses, we have these, and then over here, this picture, and so on, going around the orbit. So we can now figure out how big those, what their masses are. So this is maybe a key thing, right? So there are different types of ways that binary stars appear. We could have that eclipsing binary, where we know that they're almost aligned with our line of sight. We can see a binary on the sky like this. This is astrometric binary. We can measure the positions of the stars. But usually, this is what we see. We'll see two stars that are orbiting each other, and the evidence that they're orbiting each other comes in the spectral lines. So we'll see that, let's say, some line of hydrogen, there'll be a pair of them, and they'll move around in time. And of course, the time scale over which they move back and forth is the period of the orbit. Unfortunately, this isn't enough, because we don't know, if we knew the orbit was like this, we would know how far they had moved, given their velocity. But in principle, the orbit could be tilted, right? So if the orbit's tilted, you won't notice them moving in and out towards us as much. And we don't necessarily know whether it's tilted or whether it's how it's tilted. So here we can infer stuff about the masses of the stars, but we don't get them spot on. In this picture, we can figure out the masses spot on if we know how far away it is. And in this picture, we don't need to know how far away it is, but we can't get it spot on, except in the case where they're eclipsing, remember? Because if they're eclipsing, we know that the orbit is like this, right? So those are really treasures, these eclipsing binaries. But for the rest of them, we can figure things out. And that can tell us how do stars, why are there stars that are red and blue? And what's that range of colors during the time, in this part of the HR diagram? What is it coming from? And it's just coming from mass. So a star that's the mass of the sun, if we look at this, has a luminosity about that of the sun, right? That makes sense. But stars that are more massive, as we go up towards 20 solar masses, their luminosity goes up by a factor of 1,000,000. So the mass of the star went up by 20, but the luminosity goes up by 1,000,000. And as we go to less massive stars, they become much, much more faint, right? So the number of stars, so why we get stars of different luminosities and different colors has to do with their mass. That's the main thing that makes a difference. So if we look at the stars in our neighborhood, we can count how many stars there are of different masses. And what it shows here is that as we go to faint, lower masses, we get more and more stars. That's what this red curve is showing. Right? Now the other curves are showing how does each star contribute to the total mass of stars in the neighborhood and the light. So the light is dominated by brighter stars, right? Bright stars make more light, so they contribute more, even though that there are relatively fewer of them. So when you look out in the night sky, almost every star that you see is one of these stars that's really, really bright. Why? Because let's say it's 10,000 times brighter, which means its mass is, 10,000. I go over here, I come down, it's about 10 times the mass of the sun. If it's 10,000 times brighter, we can see it from 100 times further away than a fainter star, right? We can see that 10 solar mass star from a distance 100 times greater. Our sun, we can barely see it if it were at 10 parsecs. But a 10 solar mass star, we can see at 100 times further, 1 kiloparsec. So think about in a ball that's 100 times larger ball contains 1,000,000 times more stars, right? So even though those stars are really rare, we can see them over such a distance. So that's why when we look at the sky, the stars that we see, the bright stars that we can see with our eye, they're mainly blue and blue-white. Not because those stars are common, it's because we can see them over a great distance, okay? The other stars that we look in the sky at night, for the most part, only very few of them are lying along the main sequence. Very few of them are around the mass of the sun on the main sequence.